Hey there, it's Shannon Math Chick Myers coming at you live from San Diego, California. Today I'm looking at a famous, or shall we say infamous, related rates problem about the ladder leaning up against the house. So there's a few different situations that we will consider. The first one being just the basic, what's the velocity of the top of the ladder when the base is a certain number of feet away from the wall. Then we'll go into taking a look at the rate at which the area of the triangle formed is changing. And then finally, we'll look at the rate at which the angle between the ladder and the wall of the house is changing. We're actually going to check out what it would be here, this first one, when the ladder is 24 feet away from the wall, and then we'll be looking at, that same measure for the other situations I was talking about. Okay, so here we go. Are you ready? Fasten your seatbelts. So here we go. In a situation like this, we're just looking at this position here as the ladder is moving down the wall. So what's going to happen is, as this ladder is moving down the wall, and you see that the base has to be moving out because it's not going to be hooking in, going underground, right? So the constant here is the length of the ladder, so that will not change. So part of the trick with related rates problems is figuring out, okay, what quantities do I know, what rates do I know, and what's going to change and what isn't, okay? So here we go. Let's identify what we've got going on. So our quantities that we have are what? We know that we've got a triangle. And what do we know about triangles? We can assume that the house makes a right angle with the ground, right? So what does that bring to mind? Good, the Pythagorean Theorem, right? So in general, what is that? It's the sum of each side squared is equal to the hypotenuse squared. So instead of calling this a rate, because it is a rate, let's call this length here, we'll call, we'll just make it simple. We'll call this here y, and we will call this length here x. And those are subject to change, okay, as the ladder moves. So that's one thing that you need to think about. In a related rates problem, anything that is subject to change is something where you don't plug in a value until you get the rate, right? So that means you're going to have to differentiate before finding the rate. The 25, however, is unchanging, so you don't have to worry about that. Okay, so here we go. What do we know? So I'll call this analysis, what we're doing, meaning we're analyzing what we know, what we don't know, what we need to find, okay? So we know that our hypotenuse, right, is 25. So we'll just call it, if we have this equation, right? And so in general, we have an equation that's x squared plus y squared is equal to some c squared, right? But we know that c is always 25 because that's our ladder length. Okay, what else do we know? Well, this sentence here, the base of the ladder is pulled away from the wall at a rate of 2 feet per second. That's very important information because we've been given the instantaneous rate of x with respect to time. All right. So is that going to be increasing or decreasing? Beautiful. X is increasing as the ladder goes down. So that will be a positive rate, not a negative rate. So we will have dx dt is equal to 2 feet per second. And we found that in our problem. Okay, so we want to know what the velocity, meaning instantaneous rate of change with respect to time, the top of the ladder when the base is given below, right? So we want to find dy dt exactly when x is equal to 24 feet. So it's not saying that x is always 24 feet. It's saying that, hey, exactly when x is 24 feet, what is the velocity of the top of the ladder, okay? So we've pretty much got what we need going on here, right? All right, so now 2, well, we need to find the related equation, which we already did pretty much. And then what do we need to do with that? We're going to have to differentiate it. So the related equation, we'll just start with that, okay? Because sometimes you need to do a little bit of work on the related equation, I guess, or the, let's call it this, the related variable equation, just to be clear. Okay, so next up we have this going on. So our related variable equation was that whole x squared plus y squared is c squared, correct? But we know that c is 25 because that's the length of the ladder. So we've got x squared plus y squared is equal to what? Beautiful. 25 squared. So we're going to have x squared plus y squared is equal to, awesome, 25 squared I believe is 625. So now it might be useful to know what value y takes on when x is indeed 24 feet. Okay, we're not going to put that in right away, but it's useful to know for later. So if I isolate y, do you see I'll get y squared is equal to 625 minus x squared. And then if I square root both sides, I'll get y is equal to the positive root of 625 minus x squared. Cool so far? So when x equals 24, what do we have? Y is going to equal, and the positive root is because why? Beautiful. It's because lengths are always positive. So we'll get y is equal to, I think 24 squared, isn't it 576? So we'd have 625 minus 576, and I'm just going to double check that number. That is going to be root 49, which of course is 7. Okay, and that is in feet. But remember, we're just going to kind of hold on to that for a little bit because why? We do not want to plug it in too soon because then it's going to be meaningless. We'll like get that everything is 0. Okay? So now, next step, what do we need to do? It starts with D. It's not a bad word. Beautiful. Differentiate, because we need to find the related rates. Okay, well, in order to find the related rates, you gotta, differentiate with respect to time. Alrighty, so now let's do it. So working with this one right here, we've got x squared plus y squared is equal to 625. And then evaluating d dt of both sides, we will have d dt of our x squared plus d dt of our y squared is equal to, awesome, 0, because the derivative with respect to time of a constant is 0. So now both of these are going to be implicit, so you have to use the chain rule. So that's like 2 times x to the 1 power, and then using the chain rule we'll have dx dt, and then plus 2 times y to the 1 power times dy dt is equal to 0, which gives us 2x times dx dt plus 2y times dy dt is equal to 0. And then notice that if you divide everything by 2, or multiply, I guess, both sides by 1/2, if you will, we will get x times dx dt plus y times dy dt is equal to 0. And then now what do I need to do? I need to find out, I need to answer the question, right? So I need to find dy dt, right? So if we go ahead and we isolate dy dt, we're going to end up getting negative x times dx dt, right? And then times 1 over y. Cool so far? So I subtracted the x times dx dt from both sides, and then I divided by y, or multiplied by 1 over y. And the cool thing is we have all of those things already. But so now I'm going to actually, so now for, it really is kind of a 2-step process. So the first part of this was to differentiate with respect to t. That was our first job. And then our second job here is going to be what? Substitute in known values. Actually, substitute known values into the derivative that you found. We'll call it the derivative function. Okay, so when we do that, well, we go back to what we know. Remember that we know that dx dt is 2 feet per second from the very beginning of the problem, right? And we also know something about y. What was y? Beautiful, 7 feet, okay? So that'll give us that dy dt, which is what we wanted to find, is equal to negative. Now, x, we were interested in finding this rate when x was exactly 24 feet, right? So negative 24 times dx dt was a positive 2. And if you want, you can put in the rates because you'll see how they cancel out to give you the right unit. And then times dx dt was 2 feet per second. And then we're going to divide that by our y, which was what? Beautiful, 7 feet. So the 2 feet per second, it was our dx dt. We found y earlier, and so y is 7 feet. And then x we had found early on. That's the whole basis of the show here. So our x is the 24 feet. And now we can solve for our rate. So dy dt is going to be, it'll be negative, and that makes sense, right? Because the ladder's falling down. And then what will we have? We'll have negative 48. Do you see that one of the feets cancel, right? One of the foot units cancels. And then what is that going to be? Negative 48 sevenths. And that'll be in feet per second. And then it's always good to put a conclusion, right? So that'll be our third part here, or our fourth step, if you like steps. Put your conclusion in words. So so what is happening? The ladder actually, what did it say? The velocity the velocity of the top of the ladder, and I'm just copying down, recopying this question. Ladder is negative 48 sevenths feet per second when the base of the ladder is 24 feet away from the wall. Cool. And so that's like the official answer to our question. Okay, so our next task is to consider the triangle formed by the house, ladder, and the ground. And we want to find the rate at which the triangle, the area of the triangle is changing when the base of the ladder is 24 feet from the wall, right? So let's see, what we need. Again, we've already identified, we don't have to go into as depth on the steps. We've already identified what we know, what we don't know. We can rewrite it here. We know that dx dt is equal to 2 feet per second. We know that, I don't know that we'll need the hypotenuse this time. We're going to have a different formula, right? Our formula that we'd be using would be what? What's the area of a triangle? Area of a triangle, right, is equal to half times base times height. Well, remember we had named the height in the previous picture. We had named the height y, and we had named the base x. Good so far? And we still have that same situation as we had previously because I used the same base. So we want to find dA dt, right? Exactly when x equals 24 feet. And from the previous one, that'll be the same. That'll give us that y, again, is 7 feet from our previous work. So we've got kind of our analysis portion right here. We analyzed what we have. So now let's check it out. Our related equation is A is equal to half times base times height, right? So working with that, our area is equal to half times x times y. And then we need to find what? D dt of both sides. So, doing so, what happens, again, everything will be implicit. So dA dt is going to be, remember the constant goes along for the ride, and then we're going to have d dt of this product, xy. Be careful there. So then dA dt is equal to 1/2 times, using our product rule, we'll have d dt of x times y plus x times d dt of y. So dA dt will be equal to 1/2 times dx dt times y plus x times, awesome, dy dt. Cool? Well, dA dt is already isolated, right? So now here, well, didn't we already find out what dy dt was when x was 24 feet from the wall? So let's add this into our list of things here. We know that dy dt was equal to negative, I think it was 48/7 feet per second, right? When from our previous problem. So now let's plug in our known values, right? So dA dt will end up being equal to 1/2 times, remember that dx dt was 2 feet per second, and then y was 7 feet. Cool so far? And then x was 24 feet, and then dy dt was negative 48/7 feet per second. And so, continuing, dA dt is 7 feet squared per second plus, actually it'll be minus, so when I do the 1/2, I'll get 12 when I do that with the 24. And then I'll end up, I'm on the calculator here, I'll end up with 576/7 feet squared per second. And then subtracting, I'll have, what's that going to be? 569. No, sorry, I'm making stuff up to get a common denominator, and really we could just get a decimal, but we'll have 49 minus 576 over 7 feet squared per second. And so that will be dA dt will be 527 sevenths feet squared per second, which is approximately 75.3 feet squared per second. So to put this in the form of a, conclusion in words, look at what they asked us, right? So, and that, is negative. So now it's asking how it's changing. So what is the area doing? If it's negative, right, isn't it decreasing at this rate, right? So we would say what? In our conclusion, we could say the area of the triangle is decreasing at a rate of 75.3, actually I should say approximately 75.3 feet squared per second when the base of the ladder is 24 feet from the wall. Or from what? Yeah, from the wall. Sorry. Cool? So the last problem has to do with trig, your favorite, my favorite. So now, again, we've got this base. We're interested when it's 24 feet from the wall, okay? So now, but we're interested in finding the rate at which the angle between the ladder and the wall of the house is changing. So now this picture, we're interested in this angle, call it theta, right? That's the angle here. And so remember your right triangle trig. So we want d theta dt when x is 24 feet. So we want d theta dt when x is 24 feet. And remember, we can use right triangle trig because the house is assumed to make a right angle with the ground, right? So here, think about, all right, well, what trig function? We know this 25 right here. What trig function would work? So we know the side opposite, right, is x. And so we could do the side opposite over the hypotenuse. What is that? Good. So sine theta would be equal to side opposite theta over hypotenuse. Cool. So now what we're going to do here is work with that. Remember, we also knew that our dx dt was equal to 2 feet per second. And so I think we have what we need. So sine theta is equal to, what is our side opposite theta? Awesome, it's x. So we don't want to plug in the value for x until the end. And it's going to be x over 25. Cool? So now we just need to find our rate. So if you evaluate d dt of both sides, what's going to happen? So the derivative of sine theta is cosine theta, right? But it's implicit because this t is not the same as the theta, the variable in there. So we have to multiply by d theta dt. That's going to equal to 1/25 times, awesome, dx dt. Cool? And so now what? We'll isolate d theta dt. That's going to equal to 1/25 cosine theta, right, times dx dt. Well, what the heck is cosine theta? Cosine theta. Well, remember, we know what y is? And if you didn't, you would just find it. But we know this is y. And when x is 24 feet, we already found out that y is what? 7 feet when that happens. So, and remember that, using your triangle, cosine theta is the side adjacent theta over the hypotenuse. And so, what's that going to be? So cosine theta will be 7 over, beautiful, 25. Cool? So that's a little bit of scratch work. So now, continuing, we'll plug in the known values. D theta dt then will be, so plugging everything in, we'll have 1/25 times 7/25, and then times 2. So again, our cosine value is here, and our 7 came from up here, and all that stuff. And then the dx dt is 2, and then our d theta dt will end up being, these 25s divide out, so we'll get 2/7, and that's going to be in radians per second. So our conclusion will be what? The angle between the ladder and the house is, what's happening with that angle? Is it increasing or decreasing? It's positive, right? So it's increasing. At a rate of 2/7 radians per second when the base of the ladder is 24 feet from the wall. Cool. All right, so this wraps it up for this problem, and I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. If you like what I'm doing, please subscribe and tell your friends. Bye.